Okay, so you're going to find that in this section 6.8, it will seem like you're reviewing a lot of stuff. It really will. Now, we go probably a little bit more in depth than you did in Calc 1, but what we're doing is a different type of definition of the natural logarithm, okay? What we can do, the technical definition of a natural logarithm can be defined in terms of an integral. So this is what the definition of a natural logarithm is. Now let's talk a little bit about why this is it's basically some number greater than 0. And you should already know that, right? Okay, you can only take a logarithm of a positive number. X has to be positive, okay? But what it is we define ln x to be this integral right here. Now let's see if that makes any sense to you. Well, okay, first of all, what is the integral of 1 over t? That's ln of t, right? See, that's something that you learned already. So, yeah, that indefinite integral is ln of absolute value of t plus c. But what you're doing on this, according to this definition, you're going from 1 to x. And I'll explain why you're going from 1 to x here in just a second with this diagram. So if you're doing this integral of 1 over t dt, well, you would get ln of t. And then if you evaluate that from 1 to x, then what you would get is ln of x minus ln of 1. Okay, but what's ln of 1? 0, okay? Yeah, so you would end up getting ln of x and then minus 0, so you'd end up getting ln of x. And since we're defining this to be greater than 0, we're making a part of the definition that's greater than 0, then you don't even need that anymore. Okay, so see, that integral works out to be ln of x. Does that make sense? So what we can do is we define it, a natural logarithm, really in terms of a definite integral, so it has something to do with area. So what this diagram shows is this basic idea. Okay, now one thing that I want to show is explain what the difference between these two things is. This is, what I did on this is the graph of 1 over t. That's not the graph of the natural logarithm, that's 1 over t. So if x was greater than 1, you're doing the integral of this, and you would be getting this region right here. Okay, that would be that region right there. So, like if you were doing, say for instance, you were doing the natural logarithm of 2, and this is when x is greater than 1. If you were doing the natural logarithm of 2, what it really is it's the integral from 1 to 2 of 1 over t dt. Okay, if you work that out, you get what the exact value of the natural logarithm of 2 is. Okay, and what it represents is that area under the curve from like 1 to 2. Okay, that's what that means. All right, and that's going to be a positive area whenever you're bigger than 1, and I'll kind of give you another graph to help you understand that in just a minute. So anyway, when x is greater than 1, it's just an integral. Does that make any sense? Okay, the antiderivative of 1 over t is ln, right? So that's kind of the key thing that you want to get in your mind. Then what happens is if you're between 0 and 1, remember x has to be positive, but if you're between 0 and 1, what it means is you're integrating from 1 to x, okay, like this, but you're going to get a negative value. And if you look at the logarithm of any number between 0 and 1, you get a negative value. Okay, it doesn't mean that the area is negative. It just means since you're kind of integrating backwards from this distance to this distance, you're going to get a negative value. And that's what you have to get on a logarithm. So that's what that represents. So the idea, it would be like if you were doing the logarithm of a half, okay, that would be defined to be the integral from 1 to 1/2 of 1 over t dt. And you would get a negative answer if you did that because your limits of integration are going backwards, okay? Now, let me show you something on the calculator, and just pay attention to this. So let me clear this stuff off here and kind of give you the idea that'll help you understand this, is if I was to go through and graph the natural logarithm of x in a standard window, now this is the graph of the natural logarithm. Okay, first of all, and let me change my window just a little bit because I only need to worry about x is greater than 0. Okay, like this. Okay, so there's your natural logarithm. So if you look at this, what happens when you're past 1? What kind of answers do you get? Positive answers. What happens when you're between 0 and 1? What kind of answers do you get? Negative, okay? So basically the idea would be kind of like this. If you did an ln of 2, you're going to get a positive number. If you did an ln of something just a tad bit bigger than 1, you're going to get a positive answer. So that represents a net area that's positive. But notice if you do an ln of a fraction like 0.2, look what happens. You get a negative. So anytime you're between 0 and 1, you're going to get a negative value, okay? And the reason for that technically is just because of this. If you were doing, technically, if you were doing the ln of a half, what this really means is log base e of a half, and I'm going to set that equal to x. That would mean e to the x is equal to a half. Well, in order to get that, x would have to be a negative exponent. It would have to be, okay? So remember, it's an exponent. So when you're between 0 and 1, when this value is between 0 and 1, you got to have a negative exponent. Okay, does that make any sense? That's the abstract part of the section. That's just kind of, it's looking at the logarithm definition in a different way. You can't learn this until you're a calculus student. If you're in college algebra, you have to define a natural logarithm in a little bit different way. Okay, so what we're going to do next here is just kind of review some of the rules that we learned. We're not going to redo these. It's just we already know these. So you know that the derivative of natural logarithm of x is 1 over x. Okay, and then this is the chain rule that you learn like this, and this just means if you have a natural logarithm of a function, then what it is it's, I always think of it this way. I try to get students to learn a lot of this stuff in words. It's just 1 over the function times the derivative of the function. Okay, so that's the chain rule for a natural logarithm. So we're going to review that a little bit. Okay. Okay, so any questions with anything so far? Okay. Now, you're going to do a lot of derivatives in this section. Again, it's going to be stuff that you did in Calc 1, and some of it might be a little harder. So what you're doing on this is you're doing a log of a log. Now, what you have is this is a function. You got to look at this problem a certain way. This is a chain rule. All right, so when you do a logarithm of a function, what do you do? In words, 1 over the function times what? Derivative of function. So that's what we're going to do. The function is this, 1 over ln x. That's step 1. Then you got to multiply by the derivative of that function right there. So that's 1 over the function, ln of x, times the derivative of the function. Okay, so what do you have? You have 1 over ln x, and then what's the derivative of ln of x? 1 over x. Okay, the best way to write your answer is just multiply the fraction straight across to get 1 over x, ln of x, and then that would be the derivative of that function like that. Okay, so that's how that works out. Does that make sense to everybody? That's kind of a weird one. You have an ln of an ln. You could have an ln of an ln of an ln infinitely, and you could still use the chain rule on that. It's still basically the same idea. Okay, so that's chain rule. Now, let's look at this one. This one is a derivative. We're going to find the derivative of this function, and then this just means we evaluate it once. So once we get the derivative, we evaluate it once. So technically, we're finding the slope of a tangent line to this curve at x equals 1. So how would you differentiate this thing? Product rule. That's a product rule, isn't it? Okay, there are two functions. Okay, that's your first function. And then ln of x to the third is your second function. So product rule. We've done a lot more integration this semester than we have differentiation, so we kind of get back in the swing of reviewing this, okay? All right, now the way I do the product rule is like this. I do first times derivative of second plus second times derivative of first. Some of you do it backwards. Some of you go f prime times s plus s prime times f. That's the way this textbook teaches it. I just didn't learn it that way. I learned it backwards. My textbook, it doesn't matter. It's all the same. I just, for whatever reason, have a hard time retraining myself because of this book. So I don't care which way you do it, whatever you're comfortable with. So I'm going to do it is this way. I just write down the first, whatever it is, and then I multiply by the derivative of the second. And then I go backwards. I write down the second. And then I multiply that by the derivative of the first. So that's your product rule that you're going to put together like that then. Okay, and then from here, let's see what we have. Okay, we're going to bring down the x. Okay, then you got to be kind of careful with this derivative right here. So when you're doing this derivative that I'm doing right here, that's going to be a chain rule. So you're doing a derivative of a function. So what that's going to be is that's going to be 1 over the function times the derivative of the function. So that's a chain rule. Let me erase that and write that a little bit better. So what we're going to do is 1 over the function, okay, like that, and then the derivative of the function is what? 3x squared. Okay, so that's what that derivative right there is then. Okay, then we have plus ln of x to the third, and then of course the derivative of x is 1. So that's how that goes. Okay, everybody follow that okay? Okay. Now, it looks like what you would have on this then is, if you multiply all this straight across, and you can do this in your head if you want to, this would be 3x to the third over x to the third, and then this would be ln of x to the third. So that would divide out, so you'd have 3 plus ln of x to the third, and then you're going to evaluate this derivative at x equals 1 like that then. So that would be kind of how you start that off. Okay, any questions about that? Okay, all right, that shouldn't be too bad. You've had a background for that. Now you just do 3 plus ln, and then just kind of plug in the 1, so you'd have that. So that looks like that would be 3 plus ln of 1, and then ln of 1 is 0. So it looks like the final answer on that would be equal to 0 like that. Okay, that's the idea. Okay, so that doesn't look new to you. That's Calc 1 stuff. Okay, we're just looking at the problem a little bit differently with our definition. Any questions? Okay.
Would you get the same answer if you substituted x in the first step? Because then you basically just had ln of 1, which is 0. So
if you did what? If plugged it in when?
At the very beginning, before even doing the derivative.
Well,
What does that symbol mean to evaluate it?
Now you need to get the derivative function before you evaluate it. Now there's going to be times when it would work.
Yeah.
But it's in general you want to get that derivative, then evaluate in that order. Okay, just kind of depends on the function. So yeah, you could do that. Now see, if you plugged that in at the beginning, you would actually have 1 ln of 1. Okay, so that's off a little bit. Okay, so in general you want to get that derivative. Okay, so let's do this one more example of differentiating. We're going to get into integration also here. Okay, so the idea with this next one here is you've got a third power, and the way I like to do a problem like this is, to me it's helpful for me to see this if I write this like this. Okay, it's an ln of 3x to the second plus 2, and the whole entire thing is to the third power. Okay, that's kind of like having a sine squared of x. The whole thing would be the second power. Okay, what kind of rule do you use on that? Chain rule. Okay, that's like a kind of a power rule. You bring the 3 down, kind of like you're doing a power rule, but the chain rule is what you apply. So the first step would be, you bring the 3 down, do not touch the inside part, leave that totally alone. Step 1, and then that thing you subtract 1 from that to get 2. Then you got to multiply by the derivative of everything that's inside. So that's what the chain rule is telling you to do. So now we do the derivative of ln 3x squared plus 2 like that. So that's the setup of the problem. The structure is something to the third, so you're doing an extension of a power rule. Okay, so now what you would have, it looks like we would have from here, just kind of keep bringing things down. I have 3 ln 3x squared plus 2 to the second. Now let's focus on this derivative. So you do this in your head basically. So this is another chain rule. So how do you do a derivative of a log? 1 over the function times derivative of function. Learn that in words and it'll help you. So that's 1 over the function, then multiplied by the derivative of the function that's inside parentheses. So what's that? 6x. Okay, so there's your derivative. It's not simplified, but there's your derivative. Okay, does that look good to everybody? Okay, all right. So what I'm going to do on this is just kind of multiply everything together and then just kind of see where I'm at with this. So one thing I would have is, you could do 3 times 6x. So it looks like that would be 18x. And then I would probably just go back, and you can leave it that way if you want to, but you could probably also go back and write this as ln to the second of 3x squared plus 2, and then the whole thing on that's going to be over 3x squared plus 2, so that would be a good way to write the answer to the problem like that. Okay? Okay, everybody follow that okay? All right. Okay. So the next thing I want to kind of look at, and I'm not going to go through this too much, I'm just going to kind of explain something that if somebody was studying mathematics like as a major or something, you get into a lot of derivations and proofs and stuff. So these are properties that you would have learned like in pre-calc or college algebra, most of these, and then of course the derivative and integral rules you learned in Calc 1. But a couple of things I want to show you on this is mostly Calc 1 stuff, is this is the graph of the ln right here, and you can see it's increasing always for x greater than 0. So I want to use this just kind of an opportunity to show you how you would show that with calculus. So if you did the derivative of ln of x, you know that that's 1 over x, okay? The way you learned in Calc 1 to tell if something's increasing or decreasing is what you did is you just tried to see where the derivative is positive or negative. Derivative is positive, what is the function doing? Increasing. Derivative is negative, what's the function doing? Decreasing, okay? So basically what you would do on this is you actually could kind of analyze this by a real simple sign chart. Now x can't be 0, so you'd kind of have 0 there. Well, the thing is, if you plugged in any number that's positive into x, like 2, what would you have? You'd have 1 over 2, so you'd have a positive. So that would mean that the function has to be always increasing, because the derivative's always positive because x is always positive, right? Okay, so that would be the idea. The other thing that you learned about is probably concavity. Okay, I usually teach a little visual on concavity. Concavity has to do with the second derivative. So if the second derivative is positive, that means you're concave up. So I do that smiley face, and then I put a tattoo, a second derivative tattoo on the guy's cheek. Okay, like that. Then it goes like this. If the second derivative is negative, then you're sad. So that means you're concave down. Okay, like that. So that's an easy way to remember that.
And you tattoo his eye, and you're harsh.
Isn't that cool? Okay, I saw that in a textbook many years ago. I didn't come up with that. I'm not clever enough with that. So yeah, the eyes are negative, the eyes are positive. That's how I remember concavity. So what you do on concavity is, okay, your first derivative is x to the negative 1. Okay, that's really what y prime is. I'm going to write it that way. So the second derivative would be negative 1 x to the negative 2. Okay, so that would be equal to negative 1 over x squared. So that right there is your second derivative. Now if you analyzed this, now remember that x is always positive on a logarithm. So what would happen on this, if you plugged in any number, what would happen if you just plugged in any number on this one? You'd get a negative, wouldn't you? Okay, because you're squaring that number anyway. It's just negative 1 divided by a positive number. It's just negative over positive, so it's negative. So that means you're concave down. And you always are. You can tell by the graph that it's concave down. Okay? So that's just kind of a quick review of stuff you did in Calc 1, how you can figure out where things are increasing and decreasing without looking at the graph. Okay, so that's the idea. Okay, any question on that? You guys remember that okay? Reasonably well? Okay. All right. So the other thing is of course, we've already talked about the derivative and reviewed that. We've reviewed the integral. These are basic properties that you typically learn in like college algebra. Like you learn that the log of a product is the sum of the logs. Okay, what that means is just if you have the log of 2 times 3, that's really the same thing as the log of 2 plus the log of 3. And the way that is proved is with integrals, okay? And then you have this property that says the log of a quotient is the difference of the log. So an example of that would be like if you had log of 4 over 2, that would be ln of 4 minus ln of 2 like that. And then you got this property that we use quite a bit that would say, like, if you had ln of x to the third, that's the same as bringing that down like that. Okay, you guys remember those rules? Okay, you use that a little bit, you know, in calc that shows up a little bit, so it's good to kind of refresh your memory on how that goes. Okay, so that stuff should be stuff you've learned in the past, okay?
Yeah, why'd they put this at 6.8?
What's that?
They should have had this at like 6.1.
Well,
I mean, it's going over everything that you've done in Calculus 1, and 6.1 in this book started off with, like, not a review.
they could have. They certainly could have, but the reason the book does it this way is because they're trying to define this in terms of an integral.
Okay.
So I guess the idea is let's practice our integrals a little bit, then we can get into it. See, like I said, you really are reviewing a lot of things, which is a good thing, but you're looking at it from a different approach. And we actually do a little bit more integrals in this section. Then we do one thing at the end of this that's a little different than you do in Calc 1. All right, so let's do some integrals next here. So the idea here is we need to kind of look at this integral. Actually, this one is one that we did a little bit earlier in the past, so that's kind of another reason why they made this a little bit later in the chapter here. All right, let's look at this. Tell me, what do you think? Would u substitution do anything on this problem? Probably not. I mean, if you set u equal to x plus 1, that wouldn't be the rest of the integral. du wouldn't work. We learned this earlier in the semester. Remember what to do? Separate. There you go. That's a good one that you separate on. Okay? So what we want to do is we want to start this kind of like this. And if u substitution doesn't work, if you have a fraction and that numerator is divided into 2 or more pieces, it's a good idea to just break it up into 2 integrals. So I'm going to do the integral from 0 to 3 of 2x over x plus 1. Then I'm going to do minus. Then I'll just do minus the integral from 0 to 3 of 1 over x plus 1 times dx like that. Okay, so that would be the ideal way to do that. Now see, those 2 integrals are manageable then. Okay? All right, so if we do, if you do this one thing that you could do on this now, let's see if this would do any good. Because I think with this one, we may have to do something like a long division. So let me show you what my thought process is on that. How are you going to do that integral? U substitution? Nah.
No, you can't multiply.
See, we're kind of in the same boat. Okay? So it doesn't look like that's going to do any good. So we did learn another thing. There's another approach to this problem. You remember? Like long division. Right, long division. So scratch that idea. Okay? That was my first thought. I was just wrong. Now I see it. That's okay. So scratch that idea. Let's do long division. Okay? It's just because that integral, you're not going to be able to do anything with it. So let's go to long division. So we got 2x minus 1, and we're going to divide that x plus 1. Now you can do synthetic or long. It doesn't make any difference. Either one works on this one. So it's your call. I'm just going to do long division on that. So remember, the first thing you're doing is you're doing 2x over x, which is x, so you record the x like that. Then you multiply, so you're doing x times x plus 1, which would be, man, I'm doing some stupid things right here. God, tell me what that is. 2, that's pretty embarrassing, and I'm recording myself too, and I'm going to put it on YouTube, and it's going to be there for everybody to see. Okay? Shame on me. Okay, so that's 2. You know how I caught my mistake? Because then I had x times x is x squared, and I'm, okay, this is really screwing up. Okay, let's try again here. All right, so we have 2 times x is 2x, and then 2 times 1 is 2. Then we subtract. Okay, so when you subtract, you're doing 2x minus 2x cancels. This is really negative 1 minus 2, so that's negative 3 like that. Okay, and then that's your remainder. So what you say then is you say we have a result of 2, and remember you put that over the divisor, so you say minus 3 over x plus 1 like that. Okay, now we're in business. Okay, so see, sometimes on integrals you'll have a thought and it doesn't work, then you have to go with another thought. Sometimes you just have to try things. I don't always see immediately what the best approach is on these problems myself. So what I'm going to do now is, instead of doing it that way, we're going to do the integral from 0 to 3 of 2 minus 3 over x plus 1 dx, like that. Now that's an integral that you can do very easily, actually. Okay, so it looks like what we'd have on this is, you can go ahead and break this up, or you can just do the antiderivatives of both of these in your head. So I'm going to do that integral minus the integral 0 to 3, and then you can do like this if you want to. You can even bring that 3 out like that, so it's 1 over x plus 1 times dx, like that. Okay, now those are easy integrals to do. Okay, so what's the antiderivative of 2? 2x. Okay, I like that integral. Okay, what's the antiderivative of 1 over x plus 1? That's an ln. Okay, good. That's ln of x plus 1. Okay, like that, and that gets evaluated from 0 to 3. And remember, if you were to do the derivative of ln of x plus 1, that's just 1 over the function times the derivative of the function, so it's the same thing. So anytime you have 1 over x plus or minus something, it's just going to be a natural logarithm integral then. Okay, so now we just go ahead and crunch it out. So it looks like we're going to have 2 times 3 minus 0 there for that first part. Then over here we're going to have minus 3. Now see, that's a constant, so I just write that like that. Then I evaluate the 3 and 0. So I'd have ln of 3 plus 1 minus ln of 0 plus 1, like that. Then I just work out the details. So this is going to be 2 times 3 is 6. That looks like a 3. That's an ln of 4. You don't need the absolute value anymore. And that's an ln of 1. And then again, ln of 1 is what? 0. So that thing becomes 0. So when you put this together, then it looks like you'll have 6 minus 3 times ln of 4. Okay? And I'm going to stop there, but I'm going to show you, you could go a little further on this. Okay? So that would be, you know, like on a test or something. That's an acceptable answer. There's nothing wrong with that. But there is one other thing you could do, because that number 4. Does anybody know what another thing you could do?
Just bring 3 to the...
Write it as 2 to the second. Right? Okay? And then that allows you to do something with your exponents. So I want to review this too, because sometimes on my math lab they're going to maybe want you to go a little further than that. And that's just because it's a perfect square. So write that as 2 to the second, like that. Now what can you do with the 2? You can bring it down. See, that's a property of logs. So you'd have 6 minus 3 times 2, ln 2. So you'd have 6 minus 6 ln 2, which is okay. And you could even factor the 6 out if you wanted to. So I'm going to go ahead and take it one more step and just write it like that then, okay? And that's just because it's a perfect square. There's no law that says you have to do that, but it's nice to know that you can do that, okay? All right, so that's the idea. Okay, any questions about that integral then with anybody? Okay, that wasn't too bad. We've already learned how to do that one in the context of long division. Okay, so the next one, and most of the integrals you do in this section have something to do with logarithms. So let's take a look at tangent of 10x, okay? So first of all, the thought process on this is first of all, the integral of the tangent, there is a formula for the integral of a tangent. And it has to do with a logarithm. I don't remember it personally. I can derive it real easily. But if you looked like at a table of integrals in the back of a calculus book, you would find something for that. But I'm not going to do it that way. I'm going to use trig identities. Okay? So, what would be a useful trig identity for a tangent? There you go, sine, cosine. See, we know how to integrate a sine and a cosine, right? So the thought process on this one is going to be like this. Let's change this to sine of 10x over cosine of 10x. Okay, that's an identity. Okay, so make a note of that if you need to. Tangent of x is sine x over cosine x. You use that identity a lot in calculus when you're doing integration. Okay, now to me, this looks like a u substitution integral. What do you think? Yeah, what would be a good u? cosine. Okay? See, if you did sine, the derivative of the sine is a cosine. It wouldn't be 1 over cosine. So u needs to be the bottom, because what's the derivative of a cosine? It's a negative sign. Okay? If you do it the other way, it didn't going to work out right. Okay? So this thing right here, that whole entire thing right there, let's let that be our u. Okay? So we're going to do u is equal to cosine of 10x. Okay, then that means du is going to be what? Negative cosine of 10x, but then by chain rule, the derivative of 10x is 10, right? Oh, sine, there I go again. Okay, negative sine, okay? All right, so we got that, so that's better. All right, so now what do we have here? We got, and then got to have the dx at the end here. So we want to make sure that that matches, the du needs to match what I'm highlighting kind of in blue there. So that means what I need to do is divide by negative 10, like this, just write that as negative 1/10. So you would have negative 1/10 du is equal to the numerator or the remaining portion of that integral like there. So that means this part needs to get replaced with negative 1/10 du like that, okay? So tangent integrals, you know, typically you want to use that identity. That's kind of the basic idea. So now when we set this up, it looks like we would have the u would be the denominator. Okay, the numerator would just be the negative 1/10 du. That's a super easy integral to do. You could slide out the constant to get negative 1/10 times the integral, and you can write that as 1 over u du. So that would be negative 1/10, and the antiderivative of 1 over u is what? Ln of u, and then plus c, because it's an indefinite integral. And then what you want to do is just plug back in the u substitution is going to, of course, plug back in there, then you got it. So that would be negative 1/10 ln cosine 10x, and then plus c like that. So that would be the final answer to that integral. Okay, that one's an easy one to check. You could take the derivative of your answer, and it should take you right back to at least to this point. If you checked it, it would take you back there, and then the identity would take you back to the tangent of 10x. Okay, like that. Okay, how's that look to everybody? Okay, all right. So tangents, that's the approach. If you look in the back of the book on the integral of a tangent x, it's the ln of something. Okay, I mean it's derived from that identity. Okay. Okay, let's see what we want to look at here next then. I want to do probably one additional integral here and kind of take a look at this one and see what we can figure out on this one. Okay, now this one's got a lot of logarithms in it. Now, this one is, let's think about u substitution on this and just kind of see what we can come up with. Ultimately, you're kind of wanting this to happen. You know, this is kind of what you're after. You know, when you have, that's kind of the thought process that we're kind of working on in this section is this. So let's think about this one for a minute and see what we can come up with here. And sometimes you have to just experiment and try things, okay? What do you suggest? Any suggestion? We actually did a derivative earlier in this section that has a lot to do with this problem.
The whole bottom.
Not the whole bottom. That would be real complicated. If you did the whole bottom and differentiated that, that would be like a product rule inside of a product rule. That'd be a mess. It's a piece of the bottom. There you go. Okay. And see, the thing is, you're only going to know this sometimes if you try. Okay. So that means that what we want is we want the rest, we want du to be what I highlighted in blue. We just need to find out if it is, okay, or if it's off by a constant. So let's try that approach. Let's let the part in yellow be u. So let's write this as ln of x like that. Okay, and I think we did that same derivative earlier. So, okay, when we do this one, remember we're doing an ln of a function. So the derivative is 1 over the function, ln x, times what? Derivative of function. So the derivative of ln of x is what? Okay, remember we did that earlier in the section. So it's 1 over the function times derivative of function. So notice that that is 1 over x ln x times dx. Okay, and look at that. That's what you're left over with. So that problem was designed with that idea in mind. Okay, like that. So we've got everything that we need on this. So u is going to be this part, and then du is going to be this right there. So it's a real straightforward, turns out to be a real straightforward integral on here. Okay, so that means when you get this plugged in, you're going to have this. This whole thing becomes u, that's in the denominator. This whole thing right here just becomes du. So it's 1 over u du. That would be your integral right there. So that means that integral would have a value of ln, absolute value of u plus c. And then you can plug back in the u. So the u was this thing. So that'll plug right back in there. So we'll have as an answer ln of ln, that's an interesting answer, ln of x plus c like that. ln of ln of ln of x. Okay, that's kind of cool. All right, so that's the idea. Does that make sense? Okay, and see, sometimes when you use substitution, you got to try. You guys have done that enough now that you know that sometimes you try a u and it doesn't work. I do the same thing sometimes. Okay. Okay, so let's see. Let's do a couple of more things here. Getting down to maybe doing, let's kind of finish up maybe with, before we take a break and do a couple more integrals. Mainly, what I want to do on this is just kind of mention a couple of things on here. And this is just kind of stuff from your background. Like this is the ln of x. This is what we call the exponential function. This is y equals e to the x. You would have learned in college algebra, what's the relationship between e to the x and ln x? What do we call those functions? They are inverses, okay? So they are inverses, okay? Logarithms and exponentials are backwards of each other. They're undoing each other. They do things in reverse. And what inverses mean is all the points are backwards. So like on the ln, you have the point 1, 0. Why? Because the ln of 1 is equal to 0. On an exponential, you have the backwards point 0 to 1. Why? Because e to the 0 is equal to 1. So every point is going to be backwards. And on inverses, you probably learned at some point in time that it's symmetrical about y equals x. The reason for that is because the coordinates go backwards. That's what an inverse is. 1, 0 turns to 0, 1. Okay? The other thing I want to remind you of is this. The exponential has a domain of all real numbers. So if x can be anything because it's an exponent, but an exponent can be any number. But notice that turns into the range of the inverse. So that you flip coordinates. So the range of the logarithm is all real numbers. That means it gets infinitely high with y values, infinitely low with y values. The other thing I want you to notice is the range of the exponential is positive numbers. That's because if you take the number about 2.7 to any power, you get a positive. And then notice that the domain of its inverse is the same thing. So does that make sense? The domain and range flip-flop on inverses because x becomes y and y becomes x. Does that make sense? Okay. All right, and then let's see. We've already looked at this. Now this would be a technical definition of the number e in a little bit different way than you've seen before. So the idea would be if you did the integral from 1 to e of dt over t, you should end up getting the ln of e. Okay, well that's easy to show. That would just be the antiderivative of that is ln of t. Then if we evaluate that from 1 to e, we get ln of e minus ln of 1. And ln of 1 is 0, so ln of e minus 0 is that. And of course that ends up being equal to 1. Okay, so that would be a way to technically define the ln of e in terms of an integral. Okay, and that's kind of the point of the section is that's what a natural logarithm is it's an integral. Okay, and that's the different idea. Okay, let's see. I'm not going to talk much about the exponential. A lot of times it's written that way. I know like when I used to do some computer programming years ago, that used to be the command for e to the x was exp of x. Okay, like in certain programming languages. So that's all I'm going to mention on that. The next thing is these properties. Now, like if you're really solid into studying math and like you're a math major and stuff like that, all of these properties are just properties of exponents. They can all be proven by working with an integral. I usually don't take the time to do that in Calc 2. The book shows a few examples of that. If you're interested, you could look at a couple of proofs on these in terms of integrals. But you guys already know this. This is nothing more than just having something like x to the second times x to the third is x to the fifth. You add exponents. That's all that is. This is just if you have a fraction, you subtract exponents. This is you multiply exponents and so forth like that. Okay? Now, the number one thing that I want to kind of point out, I want to do something on this number 4 and number 5, because number 5, that property we use a lot in this section. So if you have ln of e to the x, we have the property that says we can bring that down. So that would be x times ln of e. And ln of e is 1, so that would be equal to x. Okay, so what that property says, and I think we've seen this maybe some this semester, I don't recall, but if you had something like ln of e to the 10, the answer is 10. Okay, it's whatever that exponent is. That's what that property says. Okay, then we got this property. Okay, and what this is saying is, and you'll use this a lot at the end of this section, is like, for instance, if you had e to the ln of 2, the answer is 2. That's the answer right there. Now let me show you where that comes from. You know, somebody has to figure this stuff out. It's actually very easy to show you where this statement comes from. So here, this is kind of a proof of this formula. It would go like this. If you started by just writing ln of x equals ln of x, you know that's true, obviously, right? If you wrote this in exponential form, this is what would happen. You know that the base of an ln is e, right? So if you wrote this in exponential form, you would just say e raised to this power, that's the power, would be equal to what's left over. That's where that comes from. You are taking this expression and changing it to exponential form. So it's e to this power equals x. Does that make any sense? Sometimes students get that, sometimes they don't. That's where that property comes from. Okay, it's just taking that and rewriting in an exponential form like you learned when you were doing logarithms. So what you need to know about that is when you see something like this, if you had ln of I don't care what, the answer is 10. And the other thing that's important on this is this natural logarithm has the same base as e. If that was like a e to the log base 10 of something, it doesn't work anymore. So they have to be the same. Okay, does that make sense? E and ln have to match. Okay, that's the idea. Those bases have to match.
If it's like e to the negative ln of 10, is it 1/10?
Yeah, what would happen on that if you had like, you were saying what, e to the negative ln of 10?
Yeah.
Yeah, see, you could bring that up and write that as e to the ln of 10 to the negative 1 then, right? Is that what you're thinking?
Yeah,
and then you would have like e to the ln of 1/10. So then it'd be 1/10. Okay, like that. Okay? So that works out that way. So you can bring, if you had a number in front of the e, you could bring it up, or I'm sorry, a number in front of the ln, like you're saying, you could bring it up. Okay? And you'll see that kind of at the end of the section. We'll actually do that idea a little bit there. Okay, let's do these two integrals here, and then we'll take a little break here. And that'll kind of get me through some of the integral ideas here. So let's work a little bit with these two here. Okay, so let's see. We have integral e to the sine x, secant x. Okay, thank you substitution. That's the first thing. I got a sine and I've got a secant. When you have a sine, the derivative of a sine is a cosine, right? So what's suggestions? Any suggestion? That's exactly what I'm thinking. You read my mind, okay? If you have a secant, what's 1 over secant? Cosine. Okay, you have an identity, okay? So this is an identity. You need these identities, you're going to start using these a lot. 1 over secant is equal to cosine of x. Remember, they're reciprocals of each other. So what you want to do is you want to rewrite this integral as e to the sine x times cosine x dx. Well, why did I do that? Because the connection between sine and cosine is the derivatives. The derivative of a sine is a cosine. all right? Okay, let's do u substitution. So what do you think would be an excellent idea for u? Remember, du needs to be the rest of the integral. Sine x, that's what I'm thinking, okay? All right, so we got u there. Okay, now see, the idea is, that's easy. The integral of e to the u is e to the u. That's what we're after, is an integral of e to the u. Okay, so let's let that be sine x, and then that means du needs to be what's left over, and it is. So that's kind of lucky. So the derivative of sine x is cosine x times dx, like that. So that means that thing gets replaced with du like that. Okay, so then our u integral would go like this. We would have the integral of e to the u, and then cosine x dx is just du. So this is real simple once you get that put together. So that will be e to the u plus c. And then, of course, take your u substitution, plug it back in for u, and then you got a good answer to the problem. So the answer to that should be e raised to the sine x power plus c, like that. Okay? And as you're doing a lot of these problems with homework, if time allows, do some derivatives, check your answers and stuff like that as you go. All right? Okay? Any question on that? Okay? So when you have trig functions, identities is what you use a lot of time. Okay, so let's see what we do on this one. This is a very similar integral. It's got e to the x in it. So kind of what I think of a lot of times, and it's not always, but if I see an e in an integral, my thought process most of the time is I want to turn this into an e to the u integral. That's what I did on the last one. I saw that e to a power, so I immediately thought I want an e to the u integral because it's easy. So this one, what would be a good thing for u? Square root of x. Let's try it. Okay, let's let that be the u. So that would be just square root of x, and you could write that as x to the 1/2. And then that would mean when we do du, we'd like it to be what I highlighted in blue, or close. Okay, so if we do this, du is going to be 1/2 x to the negative 1/2 dx. So that will be, I'm going to write that as 1 over 2x to the 1/2. And then that would be 1 over 2 square root of x. And you can skip, that middle step if you want to, because you can do a lot of this in your head. So anyway, what I'd have is I'd have du equals 1 over 2 root x dx. Okay, well, I want to get rid of that 2 because, we just want this to be dx over root x. So what I can do here is I can multiply that side by 2, and I can multiply that side by 2, so I get 2 du is equal to dx over root x, and then I'm ready to do my substitution then, see. So this thing that I have highlighted in blue is going to get replaced with 2 du. Okay, then we're ready to put it all together then, okay? Okay, so when we put it together, we're going to have e to the u. Okay, the dx over square root of x is going to be 2 du. Okay, so you can just think in your mind, you can kind of bring that constant out if you want to. So that is 2e to the u du. Okay, like that. And then it's real easy to finish up then. So you can finish it up from there if you want to. I'm not writing very good here. Okay, so what I'd have is integral 2 times the integral of e to the u du. So that is 2e to the u plus c. So the final answer of the problem is 2e to the square root of x plus c. And then that would check out easily if you differentiated that like that then. Okay? Okay, so those aren't too bad. The thing that you kind of learn to look for is if you have e to a power in an integral, that's generally what you think about is let x be that exponent so you turn it into an e to the u integral. Okay? That's not too bad. Okie doke, let's go ahead and do break here then. So, well, that's fine. Let me resume. Okay, so anyway, we have that. Okay, so the idea again is I'll do one more thing. So if you had like, say, 10 to the x, how do you write that? You write that as e to what? ln of 10 to the x. Like that. Just learn to do that real fast, okay? Because what happens in these problems is you get some really messy rules. And I'll be honest with you, I never remember these rules. You learn this in Calc 1. The derivative, if you're doing a derivative of log base b, this is a log other than e, of u to the x, it's u prime of x over u of x over ln of b. I don't ever remember that. Let me show you how I remember this. I derive it. It's actually super easy to derive this formula. So I'm going to show this one to you. I'm not going to worry so much about that formula right there. So if you were doing the derivative, let me just sort of show you this example. If you were doing the derivative of log b of u to the x, this is a good thing to write down too, because this formula, you're going to be like me, you're going to forget it. But if you remember the change of base formula, then it's super easy to get this formula. So the change of base formula, we got to see if you guys remember that or not. You just change this into ln of u to the x, or u of x, I mean that function, over ln of b. Okay, I'll give you another example, just kind of the side, and you can tell me if you remember this or not. So like if you were doing the log base 2 of 3, you can't do that on your calculator. What you can do is you can do ln of 3 over ln of 2. Does that look familiar? That's college algebra stuff. Again, that's change of base formula. So you just do ln of that divided by ln of base, like that. Now, if you were going to do this derivative, see, this thing right here is a constant. ln of b is a constant. So that's a constant, so it really comes out of that derivative. So you just kind of pull that out, and you would have 1 over ln b, and then you would be left over with doing this derivative, which you know. How do you do a derivative of a function? 1 over the function times derivative of function. That's the chain rule for a logarithm. So when I do this derivative, what I'm going to have is I'm going to have 1 over the function times the derivative of the function like that. Okay? Now see, that's going to essentially give you what that formula is right there. You got u prime of x, like I got there. You have ln b, and you have that like there. So if I was going to do like a derivative of something like log base 2 of 2x, okay, I wouldn't dare use that rule because I never remember it. What I would do is I would do the derivative of ln of 2x over ln of 2, and then it would be a piece of cake. Because see, ln of 2 is a constant, and then you just do the derivative of 2x. Does that make any sense? Okay? Well, you start getting into higher math and stuff, you have so many formulas, you got to come up with strategies to develop rules instead of just memorizing them. So that's what I try to do, okay? All right, so we're going to work out some integrals. I want to just kind of mention that. There is a formula right here for integrals, and this is what I'm going to do right now, is do a couple of integrals of this sort. And again, I don't remember that rule. I never do. I just know how to do these type of integrals. There's a strategy that I use on these integrals. So b is representing a number. That's not a variable. B is like a constant, like 2 or 3 or whatever. Okay? And really what happens on this one thing that'll help you remember this a little bit, is if you have the integral of e to the x dx, well, you already know that's e to the x plus c, right? But if you changed that to something like the integral of 2 to the x dx, well, it's almost the same. It's 2 to the x, but then you got to divide by the ln of 2 plus c. Okay, all exponential functions work that way. E to the x is very special, okay, because you don't have, and let me mention this too. If you're doing the e to the x dx, you know what you could really do? You really could just say it's itself over the ln of e, and you'd still get e to the x, because what's ln of e? 1. Okay, so this rule works for everything. It's just e to the x is very, very special. Okay, that's the idea. All right, so, you know, that's a rule that I can develop if I need to. But what I do on an integral like this, number 9, is instead of going through and looking up a formula, what you want to do is you want to rewrite 10 to the x as e to the ln of 10x. That's how you want to start this problem, because you can integrate e to the x easily. It's the easiest integral there is. So see, I'm just rewriting it like that. Then, if you need to, which you usually need to do that, you can bring that x down and get e to the x ln 10 like that. So what we're going to do is we're going to change this integral to the integral from -1 to 1 of e to the x ln 10 times dx like that then. Okay? Does that make sense? Okay, this is super important when you see like an integral of a number to a power, and that number is not e. Use this strategy. Okay? Now, what did I say? If you have an e in an integral, I generally have been saying you would like it to turn into e to the u, right? So let's just let u be that exponent. Let's see if we can do this by a u substitution then. Okay? So if I do that, I would have x ln 10. Okay, that's going to be the u part right there. Okay, so we're kind of hoping that du will just be dx or something close. Okay, so what's du? ln 10, right? Times dx. How come? Well, because if you do the derivative of 2x, that's 2, right? It's just the constant in front of x. ln 10 is a constant. Okay, so that's what du would be, is just that constant ln 10. Okay, well, what we're trying to do is match these things up, so that means you need to do the typical thing we do. You could divide by ln of 10, so I'm going to write this as 1 over ln 10 du is equal to dx, so then that's what gets plugged in there, is 1 over ln 10, like that, times du. Okay, so that's how the u substitution works. Does that make sense? You got to learn how to rewrite that 10 to the x as e to the x ln 10. That's the first thing. If you get there, you'll be in good shape. Okay? All right, well, we're doing a definite integral, so we might as well go ahead and adjust the limits while we're at it. Okay, so the first, upper limit is 1. So the u substitution is x ln 10, so we just do 1 ln 10. So that's going to change to ln 10. So that upper limit, we're going to change that to ln 10, like that. The lower limit, same thing, replace x with -1, so that's -1 ln 10. So I'll just change that to ln 10 like that when I do the integral then. Okay, so let's do that. Okay, so now we're set up and then we're ready to do our integral. Okay, so when we do this, we're going to be our u integral. We're going to integrate from -ln 10 to ln 10. Okay, and then we're going to be left with, it looks like, e to the u. And then the du is going to be 1/10 du, or 1 over ln 10. Now that 1 over ln 10 is a constant, so that can come out of the integration. And then that should be the integral that we ultimately go through and work out then, like that. Okay? All right, let me pause there for a little bit and see if we got anything I need to clarify, any questions about anything. Okay, so we turned it into a super easy integral, and that's the benefit of doing it this way. Okay, I didn't even look at that integral rule. I never do it this way. This is the best way to learn how to do this anyway. So what I'd have is, for my integral, I'd have 1 over ln 10. Well, the integral, the antiderivative of e to the u is e to the u. Then you're going to evaluate that from -ln 10 to ln 10 like that. Okay? Then we just need to crunch it out, the details, and then we need to kind of see what's going on then. Okay, so this is going to be 1 over ln 10. Go ahead and evaluate your limits. So that's going to be e to the ln 10 minus e to the -ln 10, okay, like that. Okay, if we do that. All right, so now we've got a few more things to do on this, and I think somebody was asking me a question. You were asking me this question. See, that's coming up now.
Yeah.
Okay, so that's kind of, I'm glad you asked that question because that comes up sometimes. So what I would go ahead and do is just write this like this. This is 1 over ln 10, then you have e to the ln 10 minus e to the ln 10 to the -1. See, that's really a -1, so that becomes the exponent, like that. Okay, and that's something you probably need to do in that problem. Again, that's just kind of basic rules of logarithms that you've learned. So now we would have 1 over ln 10. Okay, now let's see if we're catching on to this stuff now. Tell me what e to the ln 10 is. 10. right? You need to know that immediately where you don't have to think about that anymore. So that's 10, okay? Bring down the minus, okay? What's the e to the ln 10 negative 1? What's that? It's 10 to the negative 1, which is 1/10, right? Okay, so you can, write this step, or you can save a step if you want to. So that's that. So it looks like you'd have 1 over ln 10 times 10 minus 1 over 10. Then you could get a common denominator and just, work that out. So that would be 1 over ln 10. Get a common denominator there. That would be 100 over 10 minus 1 over 10. So that looks like 1 over ln of 10 times 99 over 10. Well, that's a good answer. I think the best way to ultimately write this answer is just say when you multiply straight across is 99 over 10 ln 10, and that would be the exact value of that definite integral then, like that, okay? So see, the key on that one is rearranging that 10 to the x to e to the ln of 10 to the x. And once you get that down, then that's the ideal way to learn how to do this particular type of integral, okay? Any question about anything on that? The arithmetic at the end, does that look good to everybody? A lot of arithmetic on these problems. You guys are kind of seeing that on your definite integrals, but it's not difficult. Generally, if you know your properties, you can work with your fractions okay. Okay, let's look at this next one then. And what I want to kind of look at on example 10 is this is structurally sort of a similar problem. What you got to learn to recognize on these problems is I see this 10 to the 1 over p. Just like the last problem had 10 to the x, we need to rearrange that right there, okay? We're going to try to bypass this rule right here. We don't even need to pay attention to it. So what I'm going to do is I'm going to rewrite this as e to the ln of 10 to the 1 over p. Okay, just write it that way. Then it's probably a good idea to go ahead and use that property of logarithms to write that as e to the 1 over p ln of 10 like that. And then we're going to go back into our integral and see what we have. Because see, we're trying to turn this into a e to the u integral. That's our ultimate goal. Okay, so when we go back and write this integral, we want to write this as integral from 1/3 to 1/2. And then you're going to replace this thing with this. Okay, that's the point of that. So you're going to have e to the 1 over p ln of 10 all over p squared times dp. So that's the integral that we're ultimately going to do. Okay? All right, so what should I set u equal to? What? The exponent. Remember, we want it to be e to the u. That's the goal. E to the u is our favorite integral. It's so easy, right? So what we're going to do is that's going to be u, and then we're just going to see what happens when we do du. Okay? Whoops, that's not du, that's u. Okay, so now you want to kind of focus on the du part. Okay? Did the same thing. That's u. Okay, so we're hoping that du is what I highlighted in blue. Okay? All right, so let's write this down then. We got u is equal to 1 over p ln of 10. Now it would be, if you're going to do a derivative of that, you really should write that as p to the negative 1 ln 10 like that. Because you're going to use a power rule when you do that du. Okay? All right, so you got to carefully do du. Well, ln of 10 is a constant. So just write it down. It doesn't have any bearing on the derivative, so you just write it down. Okay, then what you're doing is you're looking at, the derivative of p to the negative 1. So what's the derivative of p to the negative 1? Negative 1 p to the negative 2. So we're going to write that as times negative 1 p to the negative 2 dp this time. Now I'm going to write a couple of steps on this du. We have a negative. I'm going to bring that negative in front of the logarithm. It just looks better. And then p to the negative 2, I'm going to write that as 1 over p to the second dp. Hey, look at that. Okay, we got our goal. Goal reached, see? Okay, who would have thought? Okay, most of these problems are designed by math teachers so that they work out this way. Okay, use substitution, you have to kind of get them to work out a certain way. So the idea with this would be, is now you could divide both sides by negative ln of 10, like that. So you would end up, I'm going to write this just as negative 1 over ln 10 times du is equal now to 1 over p squared dp. And then we can go through and kind of begin to put this thing together then. Okay. Okay, any questions so far? Just on the manipulation of the u for the u substitution. All right, so let's see. When we put this together, it looks like what we're going to have. We also need to adjust our limits. I'm going to go ahead and start building the integral here. So we have e to the u, like that, and then the 1 over p squared dp is equal to this thing. So I can go ahead and put my du there. The negative 1 over ln of 10 is a constant, so you go like that. That's an integral that'll be real easy to handle. So we've got the u and we've got the dp. Okay, and that should say, yeah, I got everything set up there. Let's do the limits next here and just kind of crunch those things out, and we'll do finish up with the integral here. Okay. All right, so let's see. Let's do the limits. Okay, so let's see. Looks like we have an upper limit of 1/2. So the u substitution was 1 over p. So that's 1 over 1/2 ln of 10. What is that?
2ln.
There you go, 2 ln 10, because you're doing a reciprocal. Okay, then we got 1/3. That's going to be 1 over 1/3 ln of 10. So that's going to be 3 ln 10 like that. So those should be your basic limits of integration that we're going to do then. Okay. All right, well, let's see. Let's get everything set up now. So let's see. The upper limit was 1/2. So now that's 2 ln of 10. And the lower limit is 3 ln of 10 like that. Okay. Everybody following along okay? Okay. Once you got this part done, you got it made pretty much. So this integral is going to be negative 1 over ln 10, antiderivatives e to the u. And then we're going to evaluate that from 3 ln 10 to 2 ln 10 like that. And then we can evaluate. So this will be negative 1 over ln 10. Plug this in. That's going to be e to the 2 ln of 10 minus e to the 3 ln of 10 like that. Now, look at this part right here. Sometimes students forget this. How are you going to handle that? Bring the 2 up. Okay? Don't forget to do that. So bring that 2 up as an exponent. Bring the 3 up as an exponent like this. And you can do some of this in your head if you want to, as long as you know what you're doing. So this is negative 1 over ln 10. This is now e to the ln of 10 squared minus e to the ln of 10 cubed. Then we got it made. Okay, so what's the answer to this part right here? 10 to the second. How about this part? 10 to the third. Okay, so what you're going to end up having then is negative 1 over ln 10 times 10 to the second, which is 100, minus 10 to the third, which is 1,000. Okay, and then you work that out, and then you would end up having negative 1 over ln 10. That would be, what, negative 900. So then the final answer of the problem should be positive 900 over ln of 10. Okay, and that's where you'd get your final answer. Okay? Okay, any questions?
Can we just take a second to digest all this?
Absolutely. That's why I'm asking. Okay, because it does take a minute to digest some of this stuff. There's a lot going on here. The key thing is is the u substitution to me, is you want to make sure that you understand how I got there. And then it's just kind of the second part is making sure you can follow through all the steps I did on the definite integral when I did that. I'd say there's little properties of logarithms that show up on these problems too. Okay. Anything, anybody got a question on there? Okay. All right, have you digested? Or are you still digesting? Okay. You always want, I'm not always going to get everything perfectly clear in class, so you can always review this outside of class if you want to. Okay. Okay. Let's see. So we're going to do one last thing in this section then, and we're going to look now just at doing some derivatives. And there's a couple of derivative rules that you learn, that you typically learn, sometimes in Calc 1, but we have a general power rule, which I'm going to derive that for you in a few minutes here. So I'm going to just show you how I do these problems. Now, this is a super easy rule. What this does is that rule extends the power rule to all real numbers. The key thing is any real number will work. So in other words, what we're looking at is if you had a function like x, and that could be even to the e power, okay? If you did that derivative, the derivative works like anything. It would just be e x to the e minus 1, like you've been doing since you learned the power rule. So it works for every single real number, no matter what it is, okay? So what I'm going to do on this first one, now the answer to example 11 you can do in your head and be done in 2 or 3 seconds, okay? But I'm going to try to give you an idea of the y part on this. So I'm going to do this the long way first, and then we'll just kind of talk about how you would do that with the quick rule right there. Then I'll go back and derive this rule for you and show you where that comes from. So the first thing I want you to do on this is let's rewrite this as e to the ln of x to the pi like that. Okay, that's a big deal in this section. You want to learn how to rewrite things in terms of an exponential, okay? Then what you could do is you could bring that down and even write that as e to the e to the pi ln x like that. Okay, now we're going to do a derivative on this thing like that. So I'm going to do the derivative of e to the pi ln x. So you guys know how to do a derivative of an exponential. So let's do that and see what comes out of this. Okay, when you do a derivative of an exponential, there's 2 things you do. It's a chain rule. So it would just be itself, whatever that is, it's itself. But then what else do you got to do? You got to multiply by the derivative of that exponent, which you can do that in your head if you want to. Okay, so you got to do that. That's chain rule. So that would give e to the pi ln of x, and then what's this derivative going to be? Pi over x, right? Because pi is a constant, and then the derivative of ln x is 1 over x. So what you end up having with this problem then is you end up having like this. It looks like you would have pi e to the pi ln of x all over x like this. Now I'm going to do a little bit of algebra on this, okay? Because we're going to clean this answer up a little bit. What could you do with this pi right here? Well, that's what we've typically been doing, is bringing that up to the exponent. So let's do that and see where it leads us. Okay, so if I do that, I would have pi e to the ln of x to the pi power, all right, all over x like that. Okay, tell me what the value of that thing I just highlighted is. X to the pi. Remember, that's that property. If you have e to the ln of something, that something is the answer. So that's going to give you pi x to the pi all over x. Okay? Now, what do you do with the exponents? Like if you have x to something over x to the something. You subtract them, exactly. So you would get pi x to the pi minus 1 like that. That would be the answer. That's the long way to do the problem. Now, that's what the rule says is, and the reason for this, the proof of that general formula for x to any power just goes like this. Okay, now like if I gave you a problem on a test, and a lot of times I give a problem like this on a test, and I want you to do the derivative, you can do it that way if you like to, or you can just do it this way. Okay, we now know that it works, so basically, as long as that's a real number, bring it down, and then subtract 1 from the exponent, and you get the same answer. You'd probably rather do it that way, wouldn't you? Okay, but that's why it works. Okay, does that make any sense? Okay, so the idea is if you saw x to any power, even if it was x to the square root of 2 power, the derivative is just going to be square root of 2x to the square root of 2 minus 1, and the problem's done. That's it. Okay, everybody got that? Okay, but I'm just trying to give you the y part of where that comes from. Okay, So the next problem, you could actually you would have to do something a little bit different with that one because that sine of y is not a constant. But let me show you this. You don't have to write this down if you don't want to. I wanted to just derive this formula because I like deriving stuff. You know, in this class I can derive stuff if it's fairly simple. So the general approach to deriving this formula is very similar to what I did over here. You can rewrite this. X to the p could be written as e to the ln x to the p power like this. Okay, so you can do that. Then you can bring down the p. So that would be d over derivative of e to the p ln of x like that. Okay, so that's what we've been doing. That's the key thing that you want to make sure that you have down. Now, let's just do the derivative together. How do you do a derivative of an exponential? You do two things. It's itself times what? Times derivative of exponent. The derivative of this exponent, p is a constant, so that stays alone. Derivative of ln of x is 1 over x like that. Okay? If you multiply all this stuff together, you know, you're just kind of putting that over 1, you would have e to the p ln of x times p would be the numerator all over x like that. Okay? Then you could bring that p up to the top to get p e to the ln of x to the p over x like that. Okay? You guys follow along what I'm doing? Okay? Now, what is this thing right here? What's the value of the thing I just highlighted? X to the p. Okay, so we're almost there. So now what we'd have is you would have x to the p times p over x. Okay, and then how do you handle this part, like x to the p over x to the first? What do? You subtract the exponents, right? Okay, there's a property of exponents that says you subtract when you have a fraction. So the result is p x to the p minus 1. That's what I was trying to prove. Okay, so notice I got what I was trying to prove. So that's that formula. Okay, so anyway, what you're getting out of this is, yeah, you can do these problems the easy way, and this only holds for x to a power. That power b can be anything, any real number. Bring it down, subtract 1 for the exponent, you're done. Okay, but you've got to kind of know something about exponentials before you can derive that formula. So that's why we're doing that now. Okay. All right, any questions? Okay. All right, let's do this last problem then. This will kind of give you one more example of this. Now see, this problem right here, when you're doing this one, it's not as simple as doing this. A lot of times students are thinking, oh God, all I got to do is sine y to the y, sine y minus 1. That's totally wrong. Okay? And the reason is sine of y is a function. This rule right here only applies when the exponent is a real number. You see what I mean? It would be nice if it worked that way, but it doesn't. So you got to take a totally different approach on this one, but it's still a matter of writing this thing in terms of e. So you're going to start by writing this function as, and this whole thing can be written like this. You can write this as e ln of y to the sine y power. Okay, is everybody getting that under control? I've done that a bunch of times now. A lot of repetition because that's the key to doing these problems. Write it that way. Anytime you have something to a power, rewrite it in terms of an exponential. Okay, what can you do with the sine y? Bring it in front of the logarithm. That's a fundamental property. So you would end up having sine y multiplied by e to the ln y power like that. Okay, so that's what you would end up kind of having on the problem is that then. Okay, so what I would do from here now is I'm ready to go ahead. Now hold on, that's not right. Okay, that's totally wrong. Okay, I put it like this. You want to write it like this. That's ridiculous. Okay, it's e to the sine y times ln y like that. Okay, I even drew the arrow. Notice that it was right in front of the ln. Why I did that, I don't know. That's just stupid things. Okay, so now we're ready to do our derivative like that. Okay, All right, so what we would do from here then is, well, okay, the derivative of an exponential is what? It's itself, which would be this, and then what? Times the derivative, which this time would be d dy, of that exponent, which is sine y times ln y, like that. So that's the derivative you got to do, okay? All right, how are you going to do the derivative of sine y ln y? Product rule, exactly. That's product rule. It's product of two functions. So you've got first function and second function. So that's going to be, just keep kind of bringing down the e to the sine y ln y. That's a part of your answer. And then I'm going to do this like this. So the first is sine y, and you can just do this all in your head if you want to. The derivative of ln y is 1 over y. Then do it backwards. The second is ln y. The derivative of sine y is cosine y. So then that would be your derivative, and there ain't going to be much you can do as far as cleaning this up. I don't really see much simplification. So I'm just going to write the final answer as e to the sine y ln y, and then I'll just write this as like sine y over y. You don't really have to do that, it just looks a little bit better. Then ln y cosine y, like that. And then that would be a good answer to the problem, would just be a stop at that point right there. Okay, do you guys see the difference between example 11 and example 12? Example 11 is a piece of cake. You can do that simple rule on it. This one you can't do that product rule on. Okay, it's a little bit more involved when you're doing that then. So my recommendation is, if you ever forget on this, is just learn to rewrite these things in terms of exponentials. To me, that's the whole key. All right? Okay, so that'll kind of